Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm back to working on the Agfa Compugraphic 9000 PS, the machine that I never thought I would work on again after I first took it apart in a PC archaeology episode. Well, this is now the third episode on this thing, and what I'm going to be setting out to do is fix the main processor board, the one with the 68020 on it, which seems to be printing a fail message over the serial port, which I discovered in the last part. I want to get to the bottom of exactly what's wrong with it, and then I want to go one step further, and just like with the I/O board, I want to run custom code on the 68020 board so we can actually make it be useful versus a PostScript interpreter for a printer that doesn't exist anymore. So without further ado, let's get right to it. Before I get started with this video, just a little bit of housekeeping. I want to mention that I'm going to be at 3 upcoming VCFs, and the big news is going to be VCF in Seattle. It's called VCF Pacific Northwest. I will be there. I'm going to have a table, so I'll be having a little bit of an exhibit, bringing some stuff, including, I hope to bring the Plexus. No, I'm definitely going to bring the Plexus. So that is, well, I'll put the dates on screen. It's the beginning of May. There's also going to be VCF Southwest, which is the one in Dallas. I'll be there as well. And I'm going to be at VCF Midwest again. That's the one in Chicago. I'm especially looking forward to the VCF in Seattle because, of course, it's within driving distance, like 2.5 hours from where I am in Portland. And that means that I'll be able to show stuff, as I mentioned. So I'm looking forward to that. And if you're in the Pacific Northwest, please come and say hello. And let's make this a very successful VCF. With all that out of the way, let's get back to working on this Agfa board. I kind of can't get enough of this thing. I just want to see this thing, well, be useful, because after last week's video where I was able to get the I/O board actually running basic, I just got excited by that, and now I wanna try to fix the main 68020 board, and then maybe I can do the same thing and we can get some software running on this. So first things first, I need to try to repair this board. And to do that, I need to get this all working like it was last week. I know from the testing I did last week that without the I/O board connected, this board never actually does anything. It just sort of appears dead. I mean, it sort of gets stuck, but I've restored the I/O board back to the way it was, which means I removed that reset circuit stuff I did on the bottom. I put the original ROM chips back in, and I also reattached the 2 pins I had cut on this serial chip. I don't know if this is really necessary for operation of the I/O board when it comes to communicating with this, but I just wanted to make sure this was back in its stock configuration so we can, well, kind of go from there. Other things I have done in the meantime is I added a ground lead onto this empty socket here, so that'll be easy for scope probing. I have also fixed the power problem by no longer needing to connect this connector to this, which resulted in that voltage drop that was causing this board not to work. So I just basically cut the cable that went to the 68020 board, and I made a new harness. And yeah, you see, I just connected it to 2 Molex connectors, 5-volt rail. That way the bench power supply, which has tons of 5-volt rail capacity, can just power this board up directly. I don't even need this one to be working. So this should solve all the power problems that we were experiencing before. I have the RS-232 port connected to my computer through one of these little adapters here. It kind of shows us what the status of these LEDs are. This thing is off right now, but those lights are on because it's connected to my computer. When I power this on, the rest of those lights should come on because this is connected. And to facilitate that, I have the 8530 serial chip back in its socket with all of the pins. And I've marked which are the transmit pins. I have the printout here from last week. So I know the RS-232 port happens to be on serial port A. That's these 2 pins. And I had lifted those out so I could connect up a UART directly to it, but I should be able to just do everything through this serial port and do away with that flaky USB UART that I was using. So at this point, with the I/O board back to stock, it's connected up, the power problem should be solved, all the pins are back in, and we're connected to the serial port. When I power this on, we should get that same fail message that I was getting last week. And here in the window, we have COM2. Let's power this thing on. 3, 2, 1. Oh, there it is. Cool. And if you recall last week, some of the characters were a little bit garbled, and that was my little UART that just was not working reliably. Pretty sure through the serial port, everything is going to work perfectly. Now, since last week, I've been working with a viewer to try to reverse engineer more of the ROMs on the 68020 board to really figure out a few things. First of all, figure out what this fail message is actually telling us, because remember, that was where I left off. I didn't know what to do. And then B, I wanted to figure out if there was a way to try to access that Atlas monitor, which we had seen in the strings of when we dumped the ROM. So we know there's some kind of machine language debugging monitor on the 60020 board. And it's really just, how do we access it? Because definitely on the 8230 serial chip, both A and B ports never showed any kind of debugging when you turned it on. Well, we have leads, and I think I might know how to access that debugging console. And we have been able to figure out some really good information about the boot sequence and where this fail message that we just saw is being generated compared to where you potentially have access to the debug console and other things like that. I think the first thing I want to try to do is I want to try to access the debug console, because apparently the debug console, if we can get this to come up, is actually available before the diagnostics run that result in this fail message. In fact, they happen so early in the boot process that even if the I/O board is unplugged, the debug console should be available. And with reverse engineering the ROMs, especially the first set of ROMs, which is this column of ROMs right here, it appears that the debug console is available on the B port. And I did some work in the meantime, sort of preparing for this video. And one thing I've been able to confirm is that the A port, without a doubt, goes to the RS-232 port. And we already kind of know that because we just saw the message. But the way it does it is it goes through these two differential buffer receiver chips. This is a pair, and these two handle the RS-232 port, and these two, which are connected to the B port of the serial chip, specifically go to the RS-422 port that plugs into, sorry, I was pointing to there, but it's actually this connector. I don't have it plugged in right now, but the majority of this is the parallel Centronics connector, but then this side of this 50-pin connector is the RS-422 port, and it's connected to this pair of chips. So port B from here to there to here. Because I don't really need the I/O board, I'm going to move this out of the way, since supposedly the debug console, if it works, will come up without this. And since this board is now powered directly from the power supply, we don't have any more power problems. We don't really need this right now. Okay, so let's talk RS-422 ports. I don't really know how to interface with it in a way that works with RS-232. So I think what I'm going to do, because I already know that port B, which is what's relevant here, is going to these two driver chips, I'm just going to remove these from the board. And I'll go into detail about why I'm removing these shortly. It'll make sense in a second. All right, so on this chip, I have the line with the dash marked for the receive pin. So that's the input into the pin. And then these single pins here are the transmit pins. So that's the data coming out of this chip. And this is the B side, and this is the A side. Remember, the B side is going to these chips that happen to be right here, and we can actually test that pretty easily. Let's use my probes here. So there's the continuity beep. So I am looking for the transmit side, which is this single dash there, and it should be going to one of the pins that were on these chips here that I took out, and I can't remember which one it's going to. There it is, right there. So that's the transmit pin. I need to get a marker because I need to mark that. So we'll know exactly where I'm going to need to pick up the serial signal that's coming out of this chip once we gain access to the machine language monitor, if we do, of course. Now the receive pin should be on this upper chip because one of these is handling the signals that come out of this that go to the computer, and the other one's handling the stuff that comes in. There it is, that pin right there. So this third one down, that's the RX signal. So if I want to feed data into this chip, like say I want to type characters to it, I'll need to inject it into that pin. I mean, I could also just clip right onto there, but either way, I just wanted to mark these. Now, one reason why I wanted to remove those is because while that chip is in there, it's always driving the receive pin. There's always a signal there. So I can't just inject it. Say I want to use this little thing here, this RS-232 TTL adapter. Well, if I try to connect the transmit pin from this, so it tries to transmit into the receive pin of this, well, it's not going to work with that buffer driver in there. Well, I've now taken it out, which means I'm free to just try to inject that signal directly into that socket there. So looking at the pinout for the chip, well, we know for sure that the transmit pin wasn't doing anything when we looked at this board on the last video. I know for sure when you power this up, nothing happens. Well, it turns out from some reverse engineering of the original ROMs, and this was kind of mentioned in the original analysis that I read at the beginning of the last video, it turns out that you have to have the CTS pin clear to send for the Zilog chip, the one on port B, which is this one right here. It needs to be grounded. And what's funny is it needs to be grounded at a very specific time. The boot sequence is actually watching for that pin at a very specific time to transition from high to low. And it has to happen within a specific window of time. Otherwise, it won't engage the debug monitor. Well, of course, the question is, like, how could you make that transition at the exact right time? You're going to like monitor the bus and see where it is in execution to do that change? Well, luckily, I guess the people who designed the ROM made a provision for that. What they did is they programmed the RTS, the ready to send port B pin, this is an output from this chip, to actually go low at the right time when the CTS needs to be low as well. So what that means is I just need to connect these two pins together, and theoretically, if all things work, then we should start seeing that Atlas debug monitor on this port. So really, we'll see it on the transmit port. And I think it's 1900 baud 8N1. So RTS is a transmit pin. So I'm going to mark it like I did the TX pin, which means I'm going to mark it with just a solid, oops, that's not where I meant to put that. Okay, anyways, I'm going to mark RTS just with a solid dash like that. And CTS, which is an input pin, so very much like the RX pin, I'm going to put a dash and a dot. And that implies that the dash and the dot, which is the CTS pin, should be on this top chip here that I removed. So let's find that. There it is. And then the RTS pin should be on here. I guess it's that one right there. Just check it's not any of these other pins as well. No, just that pin right there. Okay. So according to the reverse engineering work, hooking these two lines together, which we can do on those sockets, should result in us seeing something on the TXDB line. And we can use the oscilloscope to see if that's actually happening. And theoretically, that should come out of that line even before it does any other diagnostics like the failure RAM message or the fact that it's unhappy being connected or not connected to the I/O board. All right, so I decided to use these clips, and I'll just do the CTS to RTS jump right on the chip itself. And now with the scope probe, I just need to monitor that pin, and I guess I can monitor that pin right there. Okay, we're at 1 volt per division. I'm going to set this to normal trigger mode. Let's just check to make sure it's on the falling side, because that's what we need to look for this TTL serial stuff. And I guess we're ready to go. Here we go, 3, 2, 1. Okay, well that's a whole lot of nothing, unfortunately. Let's just check again on the pin itself. That is the pin, and I think there's really nothing happening here. Zoomed in just so we can kind of see this going a little bit faster. Again, normal trigger mode. Let's power cycle this thing. And yep, we got nothing. So that was a bit of a bust. Let's check that these lines actually do change. I did look at this before, so if we go to normal trigger mode and I power cycle this, we should see this pulse. There it is. So RTS goes low for like what, 125 microseconds or so. And if we go to the CTS pin, which is the one that's also supposed to be low, and we power cycle this whole thing again, we should see that same signal. And there it is. So that's the CTS pin on port B, and yet, even with all that, we don't get anything on port B. So something is obviously missing from this reverse engineering work, unless I maybe have to like push enter. So let me get this RS-232 transceiver hooked up, and I'll get it hooked up to port B. I'll leave this little loop connected, and then maybe I can push enter on here and that will wake it up. So the level shifter is connected up. +5 volts, ground, receive and transmit. That's all you really need for this. If I turn this on now, I should see the power light come on right there. There we go, that looks good. Now we'll just connect this up. This is the RS-232 connection to my bench PC, and it is going through a no modem adapter, which is required for this particular little adapter here. So checking the serial settings, I'm going to set this to no flow control since I'm not using flow control through this little adapter. 9600 8N1, apply. Let's turn this on. Okay, I'll hit enter. Yeah, that's not doing anything at all, unfortunately. Now, what we can do to double check that this serial connection is indeed working, I'm going to look at the RX pin. That is the green clip here. And when I type characters down in the PuTTY window, there we are. They are showing up. And while I push the enter key, if we take a look at the transmit pin, which is what I'm on right now, we're getting nothing. Nothing at all. Well, there was a little something there, wasn't there? Let's turn this off. And let me unplug this blue clip that's on here. And now when we turn this on, okay, I can still transmit. Like I can push the enter key. Yeah, I'm not really seeing anything here. Even though when I go to the receive pin, you know, we're still getting our characters. But the transmit pin, nothing. I thought I saw a little like blip or something there, but I'm not sure what that was. And again, just to reiterate that the transmit pin, which is this one, I think goes somewhere like here. Yep, right there to the where there's no chip. The chip is removed. So that means there's no problem with it like getting held by something else. It's just not transmitting anything at all. I suppose just for completeness, maybe what I need to do is get this I/O board reconnected, just in case the Atlas monitor somehow needs to communicate to the I/O board and the reverse engineering work that has been done didn't quite identify that. And I'm going to plug this back into the RS-232 port because I just want to make sure that we're getting the fail message, like everything is happy here when this thing powers up. Okay, we're getting our fail messages. So jumping these two lines together, CTS, RTS, didn't somehow magically change the boot mode of this into something other than what it's always been doing the whole time. So I just plugged it back into the RS-232 transceiver thing, back onto port 2, and let's see if that somehow magically changed anything. We'll just reset this. And no, there's nothing happening at all on this terminal session. And as I type, I can see the light blinking on there, so I know that it's transmitting properly and everything is connected up to this chip. So I think the reverse engineering work that said that we'd have a monitor available now wasn't quite right. All right, so RTS to CTS, that wasn't doing anything. And I know this signal was having that low pulse. We saw it on the oscilloscope. What about RTSA? What if this one is pulsing at the exact right time that satisfies that timing requirement? And that's, of course, if the reverse engineering work that explains this Atlas monitor was correct. Yeah, let's try that. So I disconnected the I/O board, so it's no longer connected up to power or the 50-pin cable. And I now have RTSA hooked up to CTS-B, so through a longer cable. Let's see if this works. I feel like I'm grasping at straws a little bit, but who knows, maybe this will do something. Nope. No difference. And I have the I/O board hooked back up to power and the 50-pin ribbon cable. Let's move the serial port over to show us if we're getting that fail message. It is my presumption if we're getting the debug monitor, the Atlas debug monitor, we're not going to get that fail message because it should halt the boot process before it even gets to what's generating the fail message. So I just, whoops. What? No way. Wait a second, everyone. Oh, I can't even believe it. Okay, so just to reiterate, I am now connected to serial port A, the RS-232 port. I am not hooked up to the RS-422 port, which would be for AppleTalk. So, okay, let's test the idea that the I/O board is not needed for the Atlas monitor. So I'm going to unplug that, and I'm going to unplug it from power. So the I/O board is out of the equation, and let's turn this back on. And yep, no freaking way. So the I/O board is not connected. And I mean, really, well, I can turn this off. Let's remove all these wires because you only need one single wire to go into this diagnostic mode. I'll just draw it on this. It's simply bridging RTSA pin 17 to CTS-B pin 22. So we hooked these up together, which is what I've done here, and that engages the Atlas monitor. Now the problem is, of course, if you have the transceiver chip installed, I don't think that will work. And very specifically, you have to remove this top chip. That's the one that has to come out so you can inject this RTS signal back into here, into the CTS signal. Otherwise, this line driver is going to be trying to drive that signal and you'll be fighting against it. So don't do that. Just take that chip out, it's in a socket already, and then loop these together. I mean, who's going to be doing this on the planet? There's no one else who's ever going to want to try to troubleshoot one of these things ever. It's just me here in the basement. But we got the Atlas monitor. And let me turn this thing back on. Let's see exactly what commands we can do here over with the Atlas monitor. Memory configuration 4 megs out of 16. So I guess it supports up to 16 megs. Is there a question mark? A help? Current halt points. Help? Nope. I push Q and it's doing something. I don't know what. It's just counting up these bits here. I figured out a little bit of stuff. So there are several commands that dump the memory, or the memory space that is. The H command talks about halt points. It says current halt points. I guess you could set them or maybe manage them. R shows the CPU registers. Let me show you what that looks like. Looks like that. Here's a weird one. If you type Y and enter, just prints periods kind of endlessly. I don't know what this is doing. Maybe it's a RAM check. I let this run for a while and it didn't seem to ever end. There's the command T. I don't know what that does, but if you type it and you give it a value, well, that time it didn't do anything actually. Sometimes it freezes, so I have a feeling that's maybe like a trace. So you're hitting G like to go, to jump to that point. I guess what I can do is I can try jumping to 23231 and let's see if that just returns me back to the prompt, just like the trace command did. Oh, address error. And what if I do a G2323? Same thing, address error. So I don't know why trace behaved differently with one or the other. So I type G and I put in 2 and all zeros and it says monitor entered, program counter. The program counter matches line 111 emulator. What the heck is it talking about? I don't know. I really don't know. But I'm assuming this is a go, like you can jump to vectors and stuff. I just don't get what it's saying there. It appears that capital Z is like a hardware reset. So there we go, we're back at the monitor prompt. Lowercase z just drops you back at the prompt, but I'm assuming that's like a soft reset just because it's, well, the only command that seems to be case sensitive is uppercase Z and lowercase z. Everything else doesn't really matter. U and V, they just freeze, like does that. And it will sit here forever, so I have to power cycle the device. And then there's an S command, and I wrote kind of freezes but needs extra parameters. So if you type S on its own, it doesn't freeze. If you type S with that, it doesn't freeze. But if you enter another parameter like that, then it freezes. So I'm not quite sure what's happening there. Now the funny thing is normally stuff doesn't take an extra parameter. So for instance, this command here will dump the memory space. But if we exit out of there and I type this and I type a space, it immediately starts executing the command. So it doesn't accept an extra parameter. But the S command, if you hit space, it lets you type more. So I'm assuming it wants more stuff. Now there's one other command, and it's the M command, which I thought was maybe for modifying memory. But the odd thing is if you hit a space after that, it just accepts it without letting me type anything. And it does this. And I don't know if it's getting like breakpoints or what. Oh, hold on a second. Look at this. Notice it's all zeros, then it's a 1, 1, 1, 1, 1, 1. So it's almost like it's doing some kind of test, but what the heck is all this stuff? I don't know. It's the next day, and I decided to kind of think on the stuff that I saw in this Atlas monitor and try to kind of wrap my head around it. I was really thinking once I got access to the Atlas monitor, I'd be able to start reading and writing to the memory so I could try to figure out if we're actually seeing a RAM problem with that failure message. But what I couldn't really understand is I thought maybe the M command was for modifying memory, but anytime I run the M command, it starts to output this stuff, which didn't really make sense to me at the time. I have to power cycle the computer to get it out of this mode. Well, through a little bit of reverse engineering work on the ROMs, it turns out that the B, W, and L commands, they're actually interactive editors for the memory. And the M command specifically that's outputting all these weird numbers, this is actually a RAM test. Analyzing the ROM actually tells you a little bit about the way the RAM works on this system. And it seems that the RAM starts at that memory address. And what the RAM detection routine does is it walks upwards from that increment and it tries to determine the top of memory. And it does that by, of course, writing to memory and reading back to make sure that what it tried to write was actually written. And then once it gets to a point in memory where it can't write anymore, so it writes and it reads back just nothing or garbage or whatever, it knows that that's the top of memory. Very typical memory detection routine. This is used on pretty much every computer still to this day. The detection routine is actually looking for RAM up to 16 megabytes, which we know can't possibly be installed in this machine. And that's that address. So because it has 4 megabytes of RAM on it, the actual usable memory address range is from this 20 all the way up to 23FF. So let's take this address and copy it, because I can never type all those zeros properly. And let's dump that memory. So this is actually RAM we're looking at here. Looks like there's just some random bytes in it. And the reverse engineering of the ROM tells us that the B, W, and L commands are actually interactive editors. So let's try the L command, and we'll go to that same address, which we know is physically RAM, and we will try to write something C, D, E, F, 1, 2. I think that's the right number of bytes. Yes, it is. And I hit enter, and it just goes back to the prompt. If we run this same L command again, and we take a look at that, it didn't actually write what I typed in into memory. And supposedly the way this routine should work is when you type in a value to write, it should then increment automatically to the next memory location, kind of like it does if I don't try to write anything like this. I'm just hitting enter and it's just going to the next location automatically, but it's not doing that. If I try to write anything, and we'll just save this back into here, it just exits immediately. And I went ahead and I tested, and all of the routines work exactly like this. They don't actually seem to work. So we do that, and this is allowing us to add 1 byte at a time. So we type 1, 1, and we hit enter, it just exits. And again, if we run this again, 1, 1 was not written. If I just hit enter, now it's just gonna read out all those bytes in memory. I hit the space bar to exit. So there are 2 possibilities. Either the reverse engineering for the way those commands work was done incorrectly, so therefore, supposedly it's supposed to be interactive. Maybe it's not, and I'm just using them wrong. Maybe there's like a syntax problem or something like that. But there's also a possibility that maybe we're in some kind of read-only mode. Now, the 68020 does not have a memory management unit built in. The 68030 does, and this one would need an external one if it were going to have that functionality. The MMU is what's required for doing things like virtual memory, or reallocating RAM and moving it around virtually, or also write protecting or protecting memory so it can't be written to. All normal things that you need generally if you're going to be running like a Unix OS or virtual memory. Well, it turns out that through some more reverse engineering of this monitor ROM, the problem that's happening right now where I'm not able to write to memory is actually a feature in the monitor ROM. This apparently is how this works, this write protect function. There's a 32-bit value sitting in RAM at this address, and it acts as an initialization flag. Every write operation in the monitor, so that's anytime I try to use one of those routines like B or L, checks this flag first. If it's less than 2, the write is blocked and nothing happens. So it obviously just like exits the command right back to the prompt. Here's the maddening part. Right before the monitor starts up, the ROM sets this flag to 3, which should be fine because that's more than 2, but it almost immediately runs this command. So it's this AND instruction. This ANDs the value with 1, turning the 3 into a 1. And by the time you're at the prompt, this flag is already a 1. Now what we can do is we can actually check this value. I'll just copy this. So we'll do L and we'll look at this value, and there it is. It is currently set to 1. When it's set to 1, it means we're stuck in read-only mode, and there's nothing in the ROM that ever sets it to 2 or higher. Like if there was an entry point somewhere, we could use the G command to jump to that, to execute that, and potentially would change that value back to 3, putting us back into read-write mode so we could do further testing. The potential idea for getting read-write access is that if the machine actually boots into PostScript, that there's another way you can enter the Atlas monitor from that, like some kind of a vector you could jump to. And because the system is already running and writing to memory, you just have to alter that memory location to make sure it's a 3, and then when you jump into the Atlas monitor, you'll have full write access. So for us, because the system doesn't boot, obviously, we get that fail message, our real option is to patch the ROM, because there's actually this instruction right here that does this ANDing with a 1. Well, all we need to do is just change this so we AND it with a 3 instead of a 1, and that will leave that value alone, and that should give us full read-write access in the Atlas monitor right here. Well, it turns out that's only changing one single byte, and it's in one of the ROM files. So change ROM LL0, that is the first chip. It's on the bottom. You can't see it, but it's down here. And we have to change offset 298 from a 01 to a 03, and that will affect this and instruction, and add that 3 to it, and we should have write access. So I think it's time to test this theory and see if this actually is correct. So I've loaded up the LL0 ROM. This is the one that supposedly we have to patch. And let's go find, I think, what was it, 298? There it is. The offset is 298 and is currently set to 01. And at the end here needs to be 60. I just want to make sure I change this to a 03. There we go. So that's the only byte that I changed in this entire file. So it's going to be saved as U281 patched. Now we just need to load this into our EEPROM programmer. So there it is, LL0 patched. And I'll just program up one of my blank chips. And one little top tip with these older chips is sometimes it helps to write them multiple times. I don't know why, but I found that with these mini pros, or whatever this thing's called, TL something or other now, writing it multiple times can actually help. I've had issues in the past where the chip didn't always work, where the EEPROM had some issues in a particular system where it was acting flaky. Even though it would verify correctly in here, it seemed like maybe the values or the cells weren't programmed perfectly. So maybe their outputs were incorrect or something. So you can just hit program multiple times. Like this is the third time I've programmed this chip. As long as you don't have blank check actually set, which will prevent you from hitting program if the chip's not blank, you can just program the same values over and over and over again into it. So I think 5 times will be good enough. This is the chip I just programmed, and this is LL0, the one that I need to replace. Sorry, you weren't able to see that. So it's this chip right here. I just swapped it out. And if this works, when I boot the system up, we should just end up in the Atlas monitor. Everything should look the same, but I should be able to check that memory location, the one that we looked at earlier, and see that it's now a 03 versus 01. And then theoretically, the write routines should now actually work. Okay, here we go. Let's see if this actually boots up. So that was the memory location we need to check. Okay, we're still getting the Atlas monitor. So let's just run this again. Let's see if this worked. It freaking worked. So that means theoretically we should be able to write to memory now. Let's give that a try. So I'll just use, well, I'll try this one here. Potentially these bytes at the beginning of memory are used for the Atlas monitor, so I could be corrupting them or whatever, but we'll just try this anyways and see if it actually writes. I think it freaking works. No way, that actually worked. Oh, that is so freaking cool when a plan comes together. All right, so first thing I need to do is I need to reset the system here because I don't want to potentially have it act up because I corrupted the memory. Now, I mentioned this earlier that this M command is actually a RAM test that's happening and it's giving us values and memory locations of where there's a fault. So I'm going to power cycle the computer. So now we're back at the prompt, and apparently these are memory locations that are having faults. And I think what these values are trying to tell us is that it's trying to write a particular value to the memory location and it gets back something that it doesn't expect. So I think it's writing E9, E8, this, and it's getting back E9, E9, E1, D0. So why don't we try this ourselves first? So we can look at the value that's currently in this memory location, and it's currently all zeros. So there's nothing there right now. So let's try writing to this memory location. Let's try writing this to it. And if I hit the space bar and I issue this command again, let's look at what we actually wrote into it. Okay, so what we wrote actually is what we see. So that's fine, but maybe I was misreading this. Maybe what it actually wrote into memory was this, and that's what it got back. Let's just do this again. So we'll write that, and I'm going to copy this location or this value. We'll paste that in, exit out, look at this again. There we go. So I wrote E9, E9, E1, D0, and I got back E9, E8, E1, D0. So that's very, very useful, isn't it? Let's try this again, and I'm going to write just all Fs, FF, 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 FF. Okay, and now let's look at that again. Oh, I didn't think I did that incorrectly. Oh, that works actually. So you can actually just type what you want to write to memory right after the command. Anyways, so I wrote all Fs and we got back FFFE, FFFF. So the question is, if we write all Fs to the next location and the next one, and we do a bunch of these, do we have that same problem in multiple memory locations? So there's a bad bit. That's okay. Okay, so we don't have like a failure of all of the bits. we have a failure of certain bits. Well, how interesting is that? Okay, well, we can use this information now because I wrote all F's and we got back, well, one of the bits turned out to be a 0. We can use the calculator to figure out exactly which data bit that is. So if I just paste into hexadecimal the value we got back, it shows us all 32 bits of the data bus. And we can see it down here. If you click this little button, it will kind of give you a better representation. So the least significant bit, bit 0, is 1. And when I wrote all F's, every single bit here, all 32 of them, should be 1s. But our problem bit, it's right freaking there. That's a 0 when it should be a 1. So a little bit of poking around in the Atlas monitor with the help of this M command, which seems to tell us which memory locations are bad, is giving us the exact information we need to know, well, which bit isn't working properly. Is this list exhaustive? Are these all the bad bits? No, they do change all the time. Like I see 223 here, and that's 221, 220. I think what's happening is it's iterating through different patterns. These are all different patterns it's writing to the memory and then reading back. And certain cells are probably bad on one of these RAM chips that are on here. I think if we take a look at all the errors that are showing up here, every single time it's going to be this particular hexadecimal character here. It'll be the 4th over from the left. That's going to be the one that's changed. And we can just quickly eyeball that. So yes, AA, and there it's B. 2 is a 3. 6 is a 7. D becomes a C. 6 is a 7. 2 becomes a 3. A becomes a B, and so on and so forth. Yeah, pretty much just eyeballing this, everything looks exactly right. It is always 1 bit in this space right here because it's only off by 1. If the difference was like C to F, that would imply multiple bits, but it's only off by 1, which always implies that just 1 bit is wrong, and it's always in this same exact position, which pretty much tells us that it's always that bit 16. I mean, we could just put one of these into the Windows calculator just to kind of see for ourselves. So we'll use this one. So we're going to look for this bit right here, bit 16. It's currently set to 1. So now I'll copy that and we'll switch over to that value. And now it's a 0. So that again was the only bit that changed. And if we just change this manually, that changed to a 27 and a 26. And 27 and 26 is what's changing. So at least whatever RAM check it's doing here is, you know, all these random patterns, it is finding that bit 16 is the problem. Now that goes back to the question of what was that fail message that we were getting, fail to, when the system first powers up, when the monitor is not engaged? Is that a RAM test failure? And is it telling us which bit is bad as well? Well, it turns out it is actually. With some reverse engineering work of the ROMs, this is another way for us to have figured out which is the bad RAM chip. So when the machine boots, it runs a self-test before loading PostScript. If anything fails, it prints a repeating fail message on the RS-232 port. The self-test routine is actually at ROM address 84658, and it's a 2-phase test. First it does a ROM checksum, then RAM. The RAM phase writes known patterns to memory, reads them back, and compares. If it finds a mismatch, it encodes the failure code and prints it. The failure code for this board, which we saw before on the banner that was printed from the serial port, was test2 data 1010. The high byte of the 1010 decodes to RAM block 16. This is, of course, looking at the code in the ROM, and that is the 2 megabyte offset into RAM, which means bank 2 starting at address 2200000. And then the low byte is decimal 16, and the first set bit is the XOR of the expected versus actual data bit 16 of the data bus. And then when it comes to the Atlas M command with that RAM test, well, we know that it's actually this value is the written value. That's what it read back. And when you XOR those together, the exclusive OR gives you the actual bad bit. And as we already calculated manually, this works out to bit 16. Every single failing address is the same thing. Only bit 16 is the freaking problem. So this is incredible progress. We have access to the machine language monitor, and I know now where the RAM fault is. It exists in the physical chip that's connected to data line 16, and it's in the 2 megabyte bank. Now, I obviously have no idea about the way these physical chips are laid out. I just know that these are 1 bit each. So let's just theorize that this is 1 megabyte, 2 megabytes, 3, and 4, and then 5 and 6 could be added after the fact. And let's just theorize that this is data line 0, this is data line 31 of the 32 bits, and that our 16th RAM chip would be, you know, in that position somewhere in the middle here. Well, except it would be, if this is the 2nd megabyte of memory, it would be somewhere around here. I recently had a video on the second channel where I had my IBM PC 5150 with a RAM error, and I had to kind of go through this exact same exercise to try to figure out exactly which was the failure chip. And you got to make some educated guesses just based on the layout of the board, and then do some figuring out to try to see how the RAM is connected to the data bus on the CPU, and then get to the bottom of exactly which chip is the problem. If these chips were socketed, it'd be real easy. I could just take it out, move them around or whatnot, but they're all soldered. And to make things worse, these are zip packages, right? The zigzag package, I think it's called. I don't have any more of these types of RAM chips. I only have the normal 256 kilobit chips, the standard dip ones, like in this shape. Even if I find the RAM chip that's at fault, I'm going to need to make an adapter with some bodge wires to try to get this thing connected. I'll worry about that after I figure out exactly which is the bad chip. And we can test that, because if I do figure out which is the bad chip, I can just remove it from the board, and then every single bit on bit 16 in every location in that megabyte will be wrong, and the other locations in these other banks should still work. So let's go to my bunch of printouts to try to figure out exactly which is the problem. I have printed out stuff here to help us with this endeavor. So this is the zip packaging for the 1-bit wide 256 kilobit chips, where the data lines are Q and D specifically, which match up to pins 2 and 14 on the regular package. And then we know this is the floating point unit, and if we orient this in the correct way, I just have to flip this in my mind, because I know that this is like as if we're looking at the bottom of the chip, not the socket itself. Here's what we're looking for right there, data line 16. So on this socket, everything is flipped. That means data line 15, which would be that pin, is actually on the physical socket. It's going to be on that pin where ground is. So one pin should be ground, and the next one should be the data line. That should be relatively easy for me to check. Once I figure that out, just to make sure I'm correct there, then I just need to trace from here, and I can use, oh, that's funny. I can use these pins on these extra sockets, because when you look at RAM like this, all of the CAS and RAS lines are going to be common across these banks. So all the addressing RAS CAS goes this way through all the chips. But then the data lines are connected in columns. Now, the one thing I have to worry about is if the RAM is connected to the CPU directly to those data lines, or are there bus transceivers in the way? Well, I've given this board a little bit of a look over, and none of the stuff over here are transceivers. These are just sort of other types of TTL logic, probably for address decoding and multiplexing and stuff like that. The only LS245s that I see, and they got to be bidirectional, because of course the CPU is going to be reading and writing from the RAM. The only ones I can see in the general area are these chips. Now, it could well be that the RAM and the ROM exist on a data bus together that are on one side of all of these 245s, and that these are connected to the CPU and the math floating point unit. And then all of this stuff, well, this stuff could also be connected, you know, with the ROM on the RAM, or it could be connected directly to the CPU. It's really hard to say. There aren't a whole lot of LS245s on the rest of the board. There are a bunch of latches, a bunch of LS240s, which are single direction bus transceivers, or they're not transceivers, they're just drivers, because they go from one direction to the other, and that's it. They can either do that or not. They can be turned on and turned off, but they can't swap directions. So I'm gonna spend a moment just to poke around and see if the RAM and the ROMs are sharing the data bus together. Easiest way is to just look at data line 0 on the ROM chips and see if that coincides with what I see on the RAM. If those are connected together, then I can just go from those chips directly to the data lines there and see if those are connected. So I'm gonna spend a moment to kind of figure out if they're going through these transceivers and how it works exactly, because that's the key to figuring out where on this board the data line 16 is, that we know the problem is. That's the column. And once I have that, then I can think about the way the banks are hooked up. If this is 0, 1, 2, 3, or is it 0, 1, 2, 3? It makes sense to me that this would be 0, 1, 2, 3, and that's 4 and 5. And that would imply that our problem bank is this one right here. This is that second megabyte of memory, that being the first. If I was a designer, that's the way I would do it. I'm not a designer, but from my experience, that's probably the way this is done. Okay, a little bit of probing around, and I figured out exactly the way all of this RAM is connected to the data lines. So it involves these two chips. This is an LS373, which I think is a latch, and then we have an LS244, which is just a bus driver. And here's how it actually works. So there are two pins. There's Q, which is also known as data out, and D, which is labeled data in. On a lot of designs, these two pins are just connected together, but on this, they're not actually connected together. So the data out goes into the LS373, which happens to be this chip right here. It goes into the gold pin, and then it comes out that silver pin, and that actually makes its way to the CPU. So I did my testing on the very first chip on this side, which happens to be data line 0. So this is data line 0, this column of RAM chips. For the input to the chip, it actually goes from the CPU to the LS244, which happens to be this one right there. It goes into the gold pin, and then the silver pin is what comes out. So it goes into the LS244, and that comes out and it goes to the data in on the RAM chip. And it's going to go to the data in on the whole column of RAM chips. So these two chips are octal, meaning they have 8 of these types of buffers on them. So they're going to be handling the first 8 chips, data line 0 through 07. And then the next pair are going to be handling 8 through 16. Most likely, I haven't figured that out yet for sure. And then this pair right there is probably handling 16 through whatever, the next one. And our bad bit should potentially be on this pair right there. So we can confirm that by going back to our pinout, and I was looking at data line 0 before, which happens to be right there, because remember it's flipped, and now I need to look at data line 16, and that's flipped, so it's that pin. And I should be able to find that, I'm thinking, on this pair right there, and that should point us to exactly which RAM chip is the problem. Okay, so I'm on what should be data line 16, and there's our continuity beep. And this one data line makes its way, theoretically, to both of these chips. So I should be able to find this signal on one pin on each chip. There it is on the first one. That is the LS373. And let's check on the 244. There it is on that one as well. It's actually probably going to be the exact same 2 pins as this one, because this is data line 0 and data line 16 is the first bit in the bank that these are handling, because the one right here is handling up to 15, D15, but it's D16 is our problem. So it's the first bit again, and I'm sure the designers just like copy and pasted the design across. So it should be this pin right here, and it is. Okay, yeah, so the design is exactly the same as this. It's just a copy and paste of everything. So that means it's there. And the output pin that goes to the bad RAM chips is going to be there. Now I had counted up from 0 starting on this side and 0 starting on this side, that it was either going to be this chip, or rather, you know, the columns here that are going to be our problem. But I think it'll be, well, it'll be this one on the left side, because if we start at 0 and we count up, it's that chip right there. And we can tell that by just probing one of these blank pins there, and we just look on the outputs. I can't remember which is which. There we go, it's that one right there. And then the other pin, that was the D pin. Now the Q pin, which happens to be data out, should be this one right here. And it is. Okay, cool. So without a doubt, our problem chip is going to be one of these. And I'll mark them with 2 so we could tell them apart. So it's this chip, this chip, this chip, or this chip. One of those is our problem specifically. Now, it's a little bit harder for us to figure out which bank is which, because I have a feeling when the machine language monitor is running, the Atlas monitor, it's probably accessing the RAM just in its normal looping. That's probably more work than it's worth, just because we can look at this board and logically conclude that this is the first bank of memory, second, third, fourth, and then this would be the 5th and the 6th, not populated. It wouldn't really make sense that that's the first bank of memory where you could add additional memory up here. That just doesn't really make sense. So logically, we can just conclude that our bad chip is this one right here, the one I just put a silver mark on. And the way I can test that is just simply to remove it from the board entirely. And now when we do any kind of memory testing to that memory location, we should have that bit bad all the time. Meaning before we had sometimes where it was working and sometimes it wasn't, like certain memory locations were okay. Every location should be now bad with that chip out of the board. That'll confirm once and for all, that's the actual chip that we need to replace. Okay, so that means I have to try to figure out how to get that out and to get the right chip out and not pull out the wrong chip. Because, I mean, at the bottom of the board is just going to be a sea of pins. So I need to very carefully count the number of rows and columns and whatnot and take out the correct chip, mark it with a Sharpie first, use lots of hot air because this board has ground planes and power planes in it, so it wicks away the heat very quickly. But I should be able to get that out, pretty sure. And then we can kind of go from there. Yeah, I mean, look, oh, that's accidental. Look at the bottom here. It's just, there's so much stuff here. Oh boy. Sorry about that. My wireless mic was dead. I have no idea how long you were hearing backup crappy audio. So audio should be better now. Desoldering that was easy. I used hot air on the bottom side, but it's wobbling and it's loose. I just need something to grab this out. I'm going to use a little bit of needle nose. I'm pretty sure it's totally free. There it is. There's our potentially bad chip. Oh, and it's an MT RAM chip. Of course it is. Of course it is. Now what I'm going to do is I'm going to install some pin strips and just put these in offset, and then that'll allow me to put this chip back in if I need to, but then I can try to plug an adapter in so I can use a regular dip IC. It'll be ugly, but it should work. But first things first, let's test this again with that RAM chip removed, and let's look at what happens with our RAM errors when we boot this thing up. And I'll have to reconnect my little jumper link because I had it off while I was doing that work. One thing I was thinking about, by the way, is that if both of these transceiver chips were installed, I bet you the way this monitor is activated normally is there's a special cable that goes from the RS-232 connector on the back of the computer when it was fully assembled to the RS-422 that jumped those two signals together, which would then get it into the Atlas monitor. And then there would be, well, you'd plug your terminal or laptop or whatever into this, and that would give the technician access to the debug console. And I just have to see how I had this hooked up because I don't have the chip marked. There we go, Atlas monitor. It still sees the memory, but let's do the M command and let's look for those problems in the RAM. It should be way more. Okay, well, yes, this is working as expected. Now, we're only seeing the same number of bad addresses, but notice it's 0, 4, C, 14, C. It's repeating constantly, and that's going to tell us, if I turn this back on, that it's going to be every address in this space that is now bad. Oh, I think I took out the wrong chip, everyone, because the RAM error existed here at 022, not 021. That's my mistake, because the beginning of RAM, the first bank is from 0 to 1 megabyte, well, 1 byte less than 1 megabyte. And then the second bank, the one I took the chip out of, is from 1 megabyte to 1 byte less than 2 megabytes. And then our problem bank is from 2 megabytes to 1 byte less than 3 megabytes, which when we look at the board, this is from 1 megabyte to 1 byte less than 2 megabytes. This is our problem bank right there. It's the same chip in the same column, but I took out the wrong one. So I think what I'm going to do is I will reinstall this chip. I need to, but I'm going to put these little pin headers onto it and then push that back into there, solder that back in, and I'll need to go through the same process for this chip. Oh, I was not using my brain with that. I don't know what I was thinking. I should have known that I just took out the wrong chip, and I bet people are screaming at their screen that I did that. Let me fix my problem here. There we go. I've installed pin strips under both of these, so they are both in sockets. This is the bad one. That is the one that should be good, and I put back in. Let's see what happens if I power up the system. We should have the RAM error in this chip again, and then I can pull it out of the board, and we can see if we now have all the memory locations with errors. Okay, everything looks right. I want to turn this on and make sure we get our Atlas prompt. We do. Excellent. Now we issue the M command. We should see the errors at the 22 in the 22 block. Yes, we do. Perfect. It's exactly what I was hoping would happen. That means I have restored the good chip back into operation. And when we take a look at the error that we're getting, it should be, yep, E9 turns into E9E8. So we're getting the exact same bit that's bad. Let's first check this bit out again. And we know when we write all Fs, that's going to come back incorrect. And there it is. Yep, it's an E now. So let's just write all Fs into several locations. And we can just double check that that one is bad, but that one is good, good, good. So those are all good. So if I power off the system and I pull the bad chip out of the socket or the pin strips, so there it is, there's the bad chip out of the board, turn this back on. Now if we take a look at that same memory location, okay, so what should have been all zeros, it's now stuck high. So that means if we write all Fs to it, it's gonna come back as all Fs. All of these will, but we can see that it's stuck. It's always stuck high. So we take a look at this again. Yep, we're getting all Fs, which is fine. But our problem now is if we write all zeros, and now we exit out, we run this command again. Now it's coming back with the bit stuck high all the time. So I think what's happening is the LS373, the data out from these chips goes to the LS373. I think it's just registering as a high or a 1. So that means if we run the RAM test now, we're going to see RAM errors at every single location starting at 22. Not just, yeah, there we go, 0, 4C, 4C. So the same thing we were seeing when I took the wrong chip out. It is now up in the correct location, which confirms this is our bad chip right here. This is the bad one. It's not to say there's other bad chips. There could be more bad chips on here, but this one for sure is bad. So to go any further with this boot process to get the system actually loading PostScript, the only way this could possibly work is for me to make an adapter that goes from a DIP IC to this zip package, or potentially a surface mount chip. I could steal this off an old SIM, for instance, and it has to go to this pinout. I don't really understand why the zip pinout isn't just the same pinout as this chip squished together, meaning this would be A8, that would be VCC. It's not what we get. All the pins are mixed up, because if it was just this pinout squished together, all I have to do is just bend the pins to 90 degrees and I could stick the zip chip into the socket on one side and then just create little jumper links that go down to the other row of pins, and that would be it. But for whatever reason, this pinout is not that way. So I'm just gonna have to get creative and use a bunch of little thin pieces of wire and yeah, I don't know. I'll figure it out and it'll be a jump cut. All right, there's my dead bug style RAM chip mod. There are 2 pin strips that are stuck into the original socket there, so I could remove this very easily. This is not held down with any kind of glue or anything, but I think everything is correct. I used a surface mount chip, obviously. I found that the pinout of these is actually pretty similar, so it made the wiring much more easy with it flipped over like this. You can kind of see what I'm talking about, like A8 and the D line, A8 and the D line, VSS and CAS, VSS and CAS. So it's very similar, the layout between the surface mount one and this zip package. And that is the result. That's ugly, but I think it should work. I hope at least. All that's really left to do is power this thing up and then we'll run the memory test and we'll see if it passes. Okay, we got our memory configuration. Now I was thinking while I was working on this, because I had lots of time, it took a while to make this, that I won't be able to boot this system normally to see if it loads the PostScript interpreter unless we switch back to the original ROM. And that's because I think it does ROM checksums as well when it boots up. And obviously I've altered this ROM. It's not enough to affect the Atlas monitor from working, but clearly it won't go any further than that. Let's try to write to this location 2203B40 because we know that's the one where the old chip was not working. Uh-oh, that's not a good sign. It still has a 1 there. So this implies that it is still not working. So of course it's going to work all Fs because, well, I need to be able to write all zeros to it for it to actually show up, because it's possible this chip in its default configuration maybe shows up as a 1, although I'm not holding out hope. So we'll just write a bunch of zeros to this and we'll see if that actually works. I have a feeling it's not working. No, it's still stuck. All right, well, it's quite possible that I made a mistake with the wiring, so I'm just gonna have to double check my work. Very tedious. Okay, I see my problem. Ground pin, VSS, that pin is not hooked up properly. And it goes without saying that chips don't work when they are missing their ground signal. Ground should be fixed, so maybe now it'll work. All right, here we go. Hopefully nothing smokes. 3, 2, 1. Okay, got our prompt. And let's start right here. Ah, good sign. Good freaking sign. So now, yes, that was it. I mean, that chip is fixed. Let's run the M command. Maybe there's no other faults. Oh yes. I mean, this is different, right? It would give us errors right away. I don't really know how this RAM test works when all the memory is good. So I'll just let this sit here and maybe it's okay. Maybe. Oh yeah, look, it incremented. Now it has a 1 there. And now it's incremented to 1, 1. So I'm assuming all the memory it thinks is good based on the memory test that's running here in the Atlas monitor. All right, MT strikes again. That means that this chip I took out gets the X of shame. And it's pretty amazing, isn't it, that that mess of a dead bug there is actually working. That's kind of amazing to me. And we can see it's still incrementing, so that means it's working. All right, I'm going to turn this off. I'm going to remove the jumper links, and let's see if it actually can boot. Now, remember the checksum's wrong because I have this patched ROM in here. So let's see if we get a different error message on there. Maybe fail 1 for ROM checksum. Oh, wait, it's not going to work because I got to plug in the I/O board. Because I know without the I/O board, the original boot ROMs beyond that Atlas test are not happy because it sits there trying to talk to the I/O board. Okay, I have to be careful not to disturb the dead bug thing going on. Let's see what happens now when we turn this on. I can't find the power switch. Ah, here it is. Okay, yes, fail 1, which I'm quite sure is a ROM checksum error. Okay, let's switch back to the original ROM, which I have right here. Okay, the original ROM is in, the patched ROM is out, so I'll stick that there. And here we go, let's turn this on, and maybe we actually have a working system. Of course, working means what exactly? It's not like we could do anything. I mean, yeah, I don't even know how to interact with this thing. My assumption is we don't have a fail message, so it's working, but what does that mean exactly? I don't know. I really don't know. Boy, this is anticlimactic, very anticlimactic. There's probably a way to somehow get to the PostScript console, but I don't know what it is. Oh, okay. I just changed it to use flow control in the serial port settings, and then I hit enter. Some lights changed on the I/O board. I've never seen these do anything but all be on. LED 4 is on, but LED 3 was on a second ago. It just turned off, and LED 1 and 2 are off. And now we have like this PostScript error. Offending command. Yeah, GFG, that's what I was typing, and it was super unhappy. I mean, what this tells us right here is the PostScript interpreter, without a doubt, is running on this machine now. It actually is running. All right, I power cycled the entire thing. So LED 2 is flashing, which I think is the ready state. Now, doing a little reading, I think the command executive, which I'm typing in, there we go. That gives us the interpreter. Now we can actually issue commands and it echoes back what we're typing in. PostScript version 49.3, copyright 1984 through 88, Adobe Systems Incorporated, typefaces copyright, Linotype AG and or its subsidiaries. All rights reserved. We're in the PostScript interpreter. Version equals 49.3. Supposedly language level is supposed to tell us that it was level 1, but I guess maybe that's not supported. We can do math. So we can say add equals 95. So simple math problem. And here's a little loop that just counts from 1 to 5. Let's try again by counting up to 500. There it is, counting up to 500. I found a little interactive program that can actually do a little bit more. So here's a little routine for factorials. Now when I type 10 factorial and equals, then it gives us the factorial of the number. And there's also Fibonacci as well. Oh, that's making it think, or it's going to crash. Earlier I did 10 fib and that was 55. There it is. The result is 6765. That took a little bit of thinking. But that tells us there's a program in memory. All right, well, that's enough fooling around with PostScript. What have we learned here? We learned that the entire problem with this thing the entire time was the fact that it had bad RAM. And it took quite a bit of effort to get to that machine language monitor, the Atlas monitor, and then figure out exactly what was wrong with the RAM, and then me to get the RAM out of there correctly and then replace the RAM with the dead bug. And now that that's all done, we're booting into PostScript. This thing is fully operational. The hard drive is not needed. And I also never reinstalled those line drivers for the RS422, the Apple Talk port. So that's obviously not needed either. And I've also learned the 4 LEDs that are on the I/O board that have always just been solid, they actually do stuff. They're flashing and doing things to tell me the status of the engine. Based on those LEDs, it looks like it takes about a minute or so for this thing to kind of initialize itself and then get ready to accept PostScript over the serial port and presumably over the parallel port and the RS422 port as well. Now, even with all that said, and this thing is running, it's still 100% useless, right? The processor board, the 68020 board running PostScript, that really gets us nothing. So let's try to figure out a way to get it doing more so it's more useful than it is right now. In the last video, I turned the I/O board from the Agfa into something that could run BASIC and had its own machine language monitor, and that's what's in these two ROMs. So I did what you can imagine I did. I took the code from the I/O board that was on these ROMs and I altered it so it could run on the processor board. Of course, one of the big differences is this uses an 8530 for serial communication, while this uses a Motorola 68681 dual UART. Goes without saying that the RAM is in a different location on this board, and there was 4 megabytes of it versus the 16 kilobytes of SRAM that's on this board. And this, of course, has a lot more ROM space, but you'll notice I still have all the original ROMs installed, except for the first bank, the first 128K of ROM. There are some other changes that need to happen on this board. Of course, the 68020 processor, so it's a little bit different with the initialization, not to mention there's some other stuff that seems to have to be set up for this thing to actually work. But watch what happens now when I turn this on with this new custom monitor ROM installed. Instantly pops up Agfa Mod 68020. When we look at the help menu, it's got very similar functions to the last one. There is some additional features though, like now there's the ability to copy memory. And I also added Basic, which is in ROM, to have its own menu item, B. Now this works in a very similar way to the other one. You can dump memory and you can specify how much memory you want to dump. And I accidentally dumped something that's just blank. Oh, well, actually you see a little bit of code right there. And unfortunately, there's no way to break out of this because there's no stop button like there was with the I/O board, because I had the front panel working so you can push stop to abort. So you have to power cycle this computer. Maybe I should have it look for keyboard pushes while it's scrolling. That way you can push Control-C or even spacebar just to exit out of that. I always forget the exact memory location where we can start to use the memory, because part of the memory is used up for variables for the machine language monitor. And currently this thing is a little bit buggy. Like, we should be able to edit memory and it's actually not letting us do that right now. But what we can do is we can fill memory. So I'm pretty sure, I think this is the location of RAM that is free to use. Yes, it is. Okay, so let's fill that with AA and we'll do 100 bytes of it. And now when we dump that, we should see AA. We don't. I probably wrote to the wrong address. There's currently no checking to make sure that what you actually wrote to memory actually was written there. Oh, I see what was happening. I was using the fill command incorrectly. So we put fill, and we put the address. Well, let's put 00, and now we're going to put the length. It's a little confusing because I was expecting byte and then length. So now we should have the value AA in the first 100 hex bytes. And yeah, okay, there it is. So that does work. Now, just like the other ROM, there's a way to print and save S records. Unfortunately, the loading routine seems to be not working. I reassembled the Fractal assembly language code to run in the correct memory location 2050000 because the RAM location from the other board is different. Otherwise, the code is unchanged. In fact, this monitor ROM provides entry points for printing characters and getting characters, and those are at the same exact location. They work the same way as the other ROM, so that code written for the other ROM will still work. You don't have to change anything other than any kind of changes that need to happen because it's a 68020. But generally, code that runs on the 68000 will just work fine on the 68020 without any issues. Anyhow, right now the S record loader that's in here doesn't work properly. It doesn't handle the S32 records properly. Those are the ones with 32-bit addresses. It only handles the older S22 records properly. So that needs to be fixed before I can demonstrate loading any kind of software in here. Now, I did port the basic interpreter, Enhanced Basic 68000, to this machine as well. And here it is running. Of course, we have a lot more free memory, 261,000 bytes free. So I just copy and pasted the Fractal benchmark that I like to show off, and I showed in the last video running on the 68000. This is going to run a lot quicker than it did on the 68000. There it goes, speeding along very quickly. So this little basic program will render this fractal image. It is using floating point math. And of course, this machine doesn't have a floating point processor, so all of this has to be emulated. I'm pretty sure the basic itself is doing that emulation. When I ran this particular program on the I/O board running at 8 megahertz, 68000, it took 81 seconds for it to run, which actually was decently fast compared to, a lot of these other systems. But this thing running at 68020, which has a little tiny bit of cache memory inside the chip at 16 megahertz, it does it in 28 seconds. So that is about 3 times the performance of the 68000 I/O board. That's substantial. I think a lot of that has to do with the fact that this has 32-bit RAM, and of course the clock speed is double. So those two things probably combined, plus a little tiny bit of cache speed, maybe optimizations in the 68020 itself, result in that 3 times speed up. And I do have to imagine that if I had the assembly language version of this working where I could load those S records in, that ran already in a couple seconds on the other board, it would probably run as fast as 9600 bits per second could run on this thing. And if I just power cycle the computer so it's off and back on, it just in an instant, we get our prompt and the thing is up and running. Now, one of the big differences between this board and the I/O board is this thing didn't even have a serial port on it. So in order to get serial console access, I had to clip right onto this chip and use one of these little RS-232 transceiver modules so I could connect this to a computer. Of course, this has a whole bunch of ports available on it, including an RS-422 port, which I'm not using. That's channel B on the Zilog chip. And then channel A is, of course, the normal RS-232 port that I'm currently connected to. But beyond that, this thing also has SCSI. And it has two 6522s, which I know now connect up to the 50-pin cable that goes to the I/O board. Well, SCSI could be used to hook up a hard drive and actually have a proper operating system running on this thing. It's not going to be able to run any kind of operating system like Amiga OS or Mac OS. There is no display hardware available on this thing, but it would be possible to port OSs to this thing and have hard drive access over SCSI. Not to mention with the 6522s, these are general purpose I/O type chips. It would technically be possible with all the port access available on these to, for instance, add a little LCD screen to this thing and it would communicate to the screen over those connections. There's a potential to be able to hook up other accessories to these, maybe a keyboard, and in combination with a small screen, you could actually have an interactive computer without even needing to use the serial port. But I think the biggest, most exciting thing about this thing is that now that this thing is sort of understood about its memory map, where the peripheral chips are and the RAM and the ROM, it should be possible to port other things to this. And I've already been working with a viewer who is working on doing exactly that. So soon, this thing might go from being totally useless and just running PostScript to running BASIC with a simple machine language monitor to actually running a proper operating system with disk I/O subsystems so you can load and save programs. That to me is so unbelievably cool to be able to turn something that is essentially useless into, well, a cool retro single board computer, which really is what's happening even right now with just running BASIC. But running an OS, that's just chef's kiss. That will be incredible when that actually happens. How neat would it be to be able to show this off at a show like VCF, running an operating system where people could play games and stuff on it? I think that'd be amazing. A couple caveats I do have to mention, of course, is that this does not have a memory management unit, so that means protected memory is out. It also does not have remappable memory, where the memory is always at this fixed location at 20000, like what you've seen in this video. It cannot be moved to the beginning of the address space, which is very common for most 68,000 base computers. That creates a few limitations for the capabilities of what you can do on this thing, like we cannot run a full version of AT&T Unix because we need protected memory on here. That's unfortunate because it would be pretty cool, and theoretically this board as it sits here is more powerful than the Plexus simply because it's got more RAM and it has a faster processor than that thing does. But without the MMU, which that thing does have an MMU built into the board, that precludes really running at least normal versions of Unix. Anyhow, check out the GitHub repo if you want to look at that stuff. And if you're a great 68,000 coder, then please give your hand at this. And I'm more than willing to try loading ROMs onto this thing and giving it a test. Now, beyond the idea of running extra code on this, when it comes to the actual Agfa board, the processor board here and the I/O board, I really thought that this stuff was just spare parts. Never in my wildest dreams did I ever think that I would have enough information about how both of these boards work, these super obscure boards that would enable me to figure out exactly what was wrong with this main processor board and get it working. And now we have hardware descriptions of both of these boards, enough to run custom ROM code on them and BASIC on both of them. It absolutely blows my mind that someone who's just a hobbyist, and let's be honest, that's all I really am and not trained in any kind of engineering, is able to do this kind of work. And yeah, it's totally wild. So thank you very much for joining me on this journey of exploring the Agfa Compugraphic 9000 PS, a machine that was forgotten, thrown away, left for dead, and now I have, I guess, discovered more information about it than anyone has ever thought they would want to know, except for maybe the designers of this board back in the 80s. So there we go. Thumbs up if you liked this video, thumbs down if you didn't. Let me know in the comment section if you'd like to see more of this kind of stuff, because I do have other boards that are kind of mysterious like this that could use similar treatment, maybe reverse engineering of the ROMs and putting code on them and stuff like that. Huge thanks to my supporters. Names go outside the screen to make it possible to do this full time. Hit the subscribe button if you haven't already, all the other usual YouTube junk. And I guess that's gonna be that. So stay healthy, stay safe. I'll see you next time. Bye.